This is just a quick reminder that you should feel free to pause the video if you ever feel you want more time to think and write. Welcome to section 5.1, day 2, inverse functions. The real question is, how does a relation compare to its inverse on a table and a graph and with the equations? So check this out. We've got examples from the book 6 and 7. This is f of x is equal to 2x minus 3. And if you wanted to figure out what the inverse of this would be, you can change it into, say, an equation, y equals 2x minus 3, and then interchange the variables. Every time you see x, you write y, and every time you see y, you write an x. So you can interchange them like this, and then even solve. Like, let's try and get y by itself. Eventually, you get y is equal to x plus 3 over 2. And this symbol, this notation, is kind of unfortunate. You might think this is an exponent. And oftentimes it is. But in this particular case here, when you see f of negative 1, what we mean is the inverse of x. This is a special notation. This is not an exponent. So f of x is going to equal what we see up here, x plus 3 over 2. X plus 3 over 2. And so here, you can say the table, this is the original f of x. You got negative 5, negative 3, negative 1, and 1 as outputs. Well, here, when you do the table of the inverse, you get the opposite. You get the x and y values have been switched. Negative 5, negative 3, negative 1, 1 turn into inputs. And here, the outputs are this. Now you can either calculate these or just look at the tables and switch. Either way, these are inverses, and that's what it looks like on a table. Notice that this used to be a y-intercept, and now it's an x-intercept. And, of course, when you graph these, at the same time on the same graph, they are reflections of each other over the line y equals x. Notice that the function f is 1 to 1. It's always increasing. So therefore, you can say that the inverse is also a function. That's one of the things we talked about yesterday, if it's 1 to 1. If a function is 1 to 1, then its inverse is a function. Now, let's take an example 8. G of x is equal to x cubed plus 2. You might ask, is it 1 to 1? What about its inverse? Is it a function? C, is it a graph? What does the graph look like? Anyway, you can start off with a function, and if you want to figure out what g of x is, or the inverse of g of x, you have to interchange the variables. Change the x's to y's and the y's to x's, and you get x is equal to y cubed plus 2. It used to be x cubed plus 2, but now it's y cubed plus 2. Solving for y, move the 2 over, take the cube root of both sides, and then now that y is all by itself, we can just say that the inverse of g of x is equal to the cube root of x minus 2. So here, sorry for the scribbling, you've got g of x, this is the original, and you plug negative 2, negative 1, 0, 1, and 2 in, and you get these numbers out, negative 6, 1, 2, 3, 10. If you were to take those same outputs and make them inputs on the inverse, negative 6, 1, 2, 3, 10, then you would get negative 2, negative 1, 0, 1, and I want you to tell me what that last value would be here. If you were to plot them, you're plotting all these points from the tables. You see you get the original, like this, and you get the inverse, like this. Kind of feels like I have a whole lot of carbon in my throat. That's why I'm coughing so much. Carbon happens to be the 6th element of the periodic table, and that's your audio check for today. Let's take a look at the composition of inverses. You remember composition, these funny circles. Well, if f of x is equal to x cubed plus 2, and then the inverse is cube root of x minus 2, as we figured out yesterday on the previous page, or on the previous page just a few moments ago, then you might ask yourself, what is f composed of inverse of f, and what's the inverse of f composed in f? And remember what composition really is. You're just taking a function and putting it into another function. So f of inverse of f of x. Now we remember what the inverse of x is. It's cube root of x minus 2. And then if you take all of that and plug it into the original function, It's this, whatever the input, cubed plus 2. And the cube root and cube to the exponent cancel, and you have x minus 2 plus 2. And then the minus 2 and the plus 2 cancel, and you're just left with x. So if you compose, it kind of makes sense. Like if you take the input and pass it through the output, and then the output and pass it through the input, you get whatever number you start off with is the number that you're left with. A function composed in its inverse will just give you x. And here, in this particular example, we've got the inverse of f composed in f. The inverse of f it means you take the f of x function and you plug all of that in to the inverse of f function. Now f of x is x cubed plus 2, and then remember you take all of this and you put it in here. So it'll be the input minus 2, and then you take the cube root of that. That's the input minus 2, and you take the cube root of all of that. The plus 2 and the minus 2 cancel. You're left with the cube root of x cubed, and then they cancel out also, and you're left with x. You should be able to take any function and its inverse, compose them, and compose the two, and then you get just x. Just so long as the x is in the domain of each. Doesn't matter what the function is. You should be able to compose them and get x. Now, sometimes we encounter functions that are not one-to-one, and therefore the inverse is not a function. And this is one of those cases. Is it one-to-one? No. Therefore, is it an inverse function? Is the inverse of this function a function also? No. It fails the horizontal line test. You can see you draw a horizontal line, and it's not one-to-one, so therefore its inverse is not a function. But what would happen if we were to interchange the variables? You can see this is y equals x squared minus 2. You switch them up and you get x equals y squared minus 2. And then you can solve for y, and you get y is equal to, when you take the square root of both sides, you get y is equal to plus or minus the square root of x plus 2. And there is the inverse relation. And the fact that you have the 2 points here comes from the fact that it's a plus and a minus. So what would happen if you were to restrict the domain? What if we were to we know this is not going to be one-to-one, but what if we just looked at part of it and considered part of it one-to-one? What if we just ignored this half of it completely and just looked at this half right here? If we restricted the domain to only be talking about the right half of the graph, it would look like this. Now, this is one-to-one. It used to be a parabola, but we cut off the left-hand side. We restricted the domain. We said we want to look at not the original function, but the function x squared minus 2 for only inputs that are greater than or equal to 0. Bam. This is increasing always. This is one-to-one. Therefore, when you reflect this over the line y equals x, you get this, which kind of looks like a square root function. Anyway, this domain is this function with a restricted domain is, yes, one-to-one. It passes the horizontal line test. Here, the gray function, you can draw as many horizontal lines as you want, and they'll only touch at most 1 point. So is the inverse a function? Yes. It passes the vertical line test. Anyway, that's the section. I want you to start 5A2, copy the problem list, and do the first problem, and I will see you in class.